Today, I'm going to introduce the Surface-Enhanced Raman Spectroscopy, in short SERS, and maybe I can read it SERS. With the advancement of quantum chemistry, detection skill has been reached into single-molecule detection level about picomolar concentration. And one of the promising technique is SERS. Now, let's take a look briefly. First, what is Raman spectroscopy? Let's imagine that a light comes into a molecule. Then, because the light is a kind of electromagnetic wave, electron clouds oscillate along the light, generating induced dipole of molecule. This excited vibration mode soon drop into ground state, emitting an electromagnetic radiation again to the different direction, meaning that scattering occurred. So here, after Raman scattering, if the scattered light frequency is same with incident one, we call it Rayleigh scattering. But some energies can be transferred between molecule and light, making shift in scattered light frequency compared to original one. If it becomes smaller, we call it Stokes-Raman shift. But if it becomes bigger, we call it anti-Stokes-Raman shift. Therefore, we measure these frequency shifts and it shows unique material-specific peaks, providing a fingerprint of molecules. So it is useful to identify unknown molecules with Raman spectrum, and unlike infrared spectrum, Raman can measure non-permanent dipole molecule and is insensitive to moisture and temperature, showing small noise. But its magnitude is very small that only 0.0000001% of incident lights are usually scattered, so it needs to be amplified for more applications. Here, the SERS is an advanced way to measure Raman spectrum. It amplifies the Raman signal up to 10 to the 6th compared with original Raman magnitude. It can dramatically improve the sensitivity of Raman spectroscopy. So how to do that? Simply, it needs two things, a plasmonic nanostructure and an absorption of analyte molecule on that surface. Although it is not clarified yet, there are two main theories for SERS. Let's see the first one, the electromagnetic theory. In metal, when electromagnetic wave comes, the collective oscillations of free electron gas occurred along the light wave, called plasmon. It is a kind of quantum of plasma oscillation as we did in the black body, or like phonon, which is quantized particle of mechanical vibration. And especially at the metal surface, there is no positive charge above the electrons unlike in the bulk, so the electron clouds can extend considerably from the surface by electromagnetic wave, making larger oscillation called surface plasmon. As a result, this surface plasmon amplifies the electric field locally near the surface. We can understand this as the light is captured and stored at surface in the form of local electric field. And this huge electric field amplifies the Raman signal of molecule. Then, what is needed for the better plasmonic surface? The answer is the roughness. At any point on the surface, the average electric field can be divided into one perpendicular to the surface and the other one parallel to the surface. For the parallel electric field, it just oscillates along the incident electromagnetic wave and not affects the light direction. Only absorption can occur. But the perpendicular term can change the direction of light, meaning scattering occurs, so the perpendicular term should be greater for amplifying Raman. Therefore, the rougher surface will have the larger vertical area, the more electrons oscillating perpendicular to the surface, the more scattering, the bigger electric field, and the bigger Raman signal. If we take one more step, the researchers have found experimentally that the electromagnetic enhancement improved dramatically between the nanoparticles rather than just on the surface. They call it hotspot. So, to make many hotspots, they use nanoparticles aggregation, electrochemical roughening, or depositing metal onto a surface to increase roughness. Now let's see the second one, the chemical theory. It is much simpler than electromagnetic theory that when the analyte molecules are adsorbed on the surface of metal, A new chemical bond is formed between metal atoms and analytes, making the charge transfer possible from metal to the analyte. This phenomenon increases the polarizability of molecule and enhances the Raman signal. So that's it. You can find some experimental evidences for both theories, and the electromagnetic enhancement is commonly considered to be more dominant for SERS than the chemical one. The SERS is expected to be broadly used in single molecule detection, such as biosensor of proteins and biomarkers for disease diagnosis, archaeological research, forensic science such as drug detection, and even in pharmaceuticals. One interesting thing is that there is no mutual exclusion in SERS, because for SERS, the symmetry can be broken as the molecules adsorbed on the rough surface, and it makes both dipole moment and polarizability change possible, showing additional modes in Raman spectrum. In conclusion, the SERS is one of the promising techniques for single molecule detection and have many potential to be utilized in various fields such as biosensor, food quality analysis, etc. Nowadays, the enhancement of sensitivity level is almost done, and the next step will be the multiplexing analysis using SERS. I hope that this video may help you guys to know the SERS briefly. Thanks for watching.